Multi-level pool, canal system, for lift irrigation. Objective, modernization and automation of canal system. Scientific approach to crop watering and water management. To save water and energy. To get maximum yield from less water use. And equal water sharing among users. Design review. The conventional system.
As per conventional design, the FSD should be constant in all reaches, provided 24/7 pumping is done throughout the season with all the distributary outlets opened under standard condition without water losses by illegal pumping by farmers or diverting to escape channel. And during no demand, water has to be diverted to escape channels. As all the outlets were closed down, if not diverted to escape channel, water will top up the canal section at the tail end, or it has to be let go to natural streams from outlets, thereby wastage of water. As well as on every fresh run of pump, the FSD has to rise from zero to maximum level, as it is gaining its level in initial reaches towards tail end, thereby a variation in head is observed, till it is totally filled up the section. Meanwhile some of the outlets operate, some will not. So FSD is not constant, it is sinusoidal in nature, whenever pumps go on or off. In this example, travel time with 0.75 meter per second velocity of water will take 18 hours 31 minutes to reach 50 kilometers.
Demerits. The conventional system.
Demerits of conventional water conveyance system for lift irrigation canals. Full supply level is not constant, as 24/7 pumping is not practiced throughout the season. The fluctuating water level, due to on or off of pumps, or number of pumps running, is less than the design numbers pumps to run. Distributaries outlets function under design discharge, as depth of water in canal is under the mark of 2/3 FSD, as driving head is not available. If no demand, water is wasted by letting out water through escape channels, else field irrigation channels were diverted to natural drainage streams by farmers. Due to pump go on or off before FSD in canal raises to design level, the water is discharged to outlets, so tail end never reach designed FSD mark. If outlets not operated in time, due to more discharge at tail end, overtopping of water may occur. If operated prior, the FSD of the tail end doesn't gain head. If manipulated the head by operator and resolve the complexity of operation, then pumps go off. In this struggle to have control over outlets and FSD level, which leads to management failure.
Demerits of conventional water conveyance system to fields and farmers. Traditional farming methods and water tax system lead to over-irrigate. Frequency of irrigation isn't scientific, soil never get aerated. Extra water is drained by soil, thereby lot of water is wasted. Over-irrigation leads to waterlogging, low yield and salinity of soil. Quantity of water shared by head channel farmer and tail ender differs. Water isn't available when crops demand, else supplied behind schedule. Unequal water distribution leads to competition among farmers and social injustice. Concept. A solution to all the conveyance problems. Presented by Riaz Jagadal, Assistant Engineer.
Tank filling. Water filled in one tank rises the water level in another tank, and if orifice opened, empty at same time in both tanks. Water filled in one tank and discharge in another keep both water level at constant. Fluid flow from orifice can be measured. Closing the orifice again, water level in tank rises. Tank fill time. Multi-level pool, water conveyance system.
Time required for fluid transfer from one full tank to another empty tank. Assume a rectangular section for easy calculations. Size 5 meter by 2 meter. Length of tank is equals to 10 kilometers. Orifice size is 5 meter by 1 meter. Time for partially submerged orifice with average velocity, we get T1 equals 0.76 hours. And for fully submerged condition, the logic behind the formula is that, when two vessels, containing liquid, are connected together by means of an orifice, the liquid will flow, from the vessel with a higher level, to the vessel with a lower level, irrespective of their areas. In such a case the liquid level will fall in one vessel, with a corresponding rise in the other. The orifice, through which the flow takes place, is a drowned one and the liquid head, causing flow will be the difference between the two liquid levels. We get time T2 equals 1.045 hours for head difference 1 meter to 0 difference in head, that is water is standstill in both pools, as one pool reads 0.5 meter and another 1.5 meters. A total T equals 1 hour 48 minutes. And volume of water transferred is 75,000 cubic meter at discharge rate 11.51 cubic meter per second.
Let us calculate time required for tank water transfer from one full tank to another partially filled tank. Assume rectangular section for easy calculations. As said earlier, orifice fully submerged. T equals 1.4781 hours. As calculated by formula. For transfer of water from one vessel to another. Here time required to transfer water under gravity with varying head from 2 meters head difference to 0 meter is 1 hour 28 minutes. Q equals 50,000 cubic meters of water transferred. And the water level in both pools are at same level when there is no discharge from orifice. As one tank read with 1 meter head and another with 2 meter head, as standstill. Time required for tank water transferred from delivery chamber to any tank or pool in any reach. Assume rectangular section for easy calculations, as said earlier with same dimensions. Here head is kept constant in all the pools. 3 gates are opened, so that discharge from the orifice should match with the inlet discharge in the delivery chamber. If delivery chamber is discharging at the rate of 15.5 cubic meters per second, where orifice discharge is 18.79 cubic meters per second on higher side at 2 meters head difference to 13.28 cubic meters per second at 1 meter difference. Okay, we will adjust the orifice to discharge 15.5 cubic meters per second till lower pool is not filled. We calculate time. Now, wait, here head is not varying, but downstream water level increasing, thereby reducing the difference in heads of both pools, so discharge at 1.9 meter head difference is Q equals 18.31 cubic and at 1 meter head difference is Q equals 13.28 cubic, but we assume, as we control the constant discharge at 3 orifice for easy calculations, as it is constant head, constant discharge. Again, we get the answer, by total volume to be filled, divided by rate of fill which gives us time. Okay, we got T equals 0 hours 48 minutes to rise the water level from 1.1 meters to 2 meters, that is FSD level in fourth tank, with Q equals 45,000 cubic meters of water transferred. Here point to be noted is there is no travel time required. Using hydraulic calculator we study the flow properties. Let us assume a rectangular section channel. Let us calculate. For flow discharge rate of 21 cubic with bottom width 5 meters and outlet height 1 meters. Near outlet the velocity equals 4.2 meters per second. We get a jump of 0.462 meters with velocity 2.8 meters per second and Froude number between 1.3 to 0.7. That is flow is supercritical to subcritical flow. That means the velocity is reducing and flow from turbulent towards laminar flow.
Design of distribution system, quantity of water and time required in field. Consider border strip irrigation. Using field irrigation channel, bottom width equals 0.3 meters and depth of flow equals 0.15 meters, side slope 1:1, and discharging at the rate of 50 liters per second on head of strip. Time required for 10 meter by 100 meter strip to irrigate with 10 millimeters water depth with soil infiltration rate at 25 millimeters per hour works out to be 3.58 minutes. And volume of water used is 10 cubic meter, and supplied is 10.18 cubic meter with field efficiency of 98.2%. If a block is of 40 hectares, with 1,000 square meters each strip, then number of strips in a block equals 400. Total time required for one block to irrigate is equal to 3.58 minutes into 400. That is equals 1,432 minutes, means 23.93 hours, with 4,073 cubic meter of water used per block, with core depth equals 10 millimeters. Consider, if a distributory consists of 20 blocks of 40 hectares, that is, 800 hectares ICA, then required discharge rate of distributory has to be 50 into 20 equals 1000 liters per second, means 1 cubic meter per second. Volume of water supplied in 23.93 hours to 20 blocks, that is 800 hectares of land, with 81,466 cubic meter volume of water. If one pool is 10 kilometers long with 3,200 hectares of ICA, with section 5 meter by 2 meter, consider 90% water depth used by 4 distributory with 800 hectares ICA each. Then number of times pool is filled equals total water volume used for 4 distributory divided by tank size, that is equals to 3.62 times in 24 hours. Time required for each pool filling is 1.61 hours, at the rate of 15.5 cubic meter per second. Total time for 3.62 filling is equals 5.82 hour per day per pool. Number of pools alternatively filled by pump in one day with 18 hours working and 6 hours pumps rest time equals to pumping hours divided by time taken by one pool to fill in one day, that is equals to 18 hours pump run, including raising main filling time, divided by 5.82 hours. We get answer as 3 pools per day, that is 30 kilometers stretch, with ICA, 9,600 hectares with 10 millimeters core depth for one day pump operation. So we can now calculate core watering frequency. If crop core watering depth is 150 millimeters, ICA equals 9,600 hectares, with 30 kilometers reach, pumps run for 15 days during full month. If canal is 60 kilometers and ICA equals 19,200 hectares, pumps run for full month. With identical crop on the whole ICA, if mixed crop and variable core watering depths, then less depth more ICA, more depth less ICA can be created during peak demand. For 10 millimeters core depth for one day pumping for 30 kilometers ICA is 9,600 hectares, like that for 60 millimeters, or 120 millimeters core depth, 6 days and 12 days respectively, pumping needed, for said ICA. Core depth 160 millimeters for 1 month, ICA, is equals to 18,000 hectares, like that, for core depth 125 millimeters for 1 month, ICA, is equals to 23,040 hectares. For mixed crop, with different core depth, and, with different ICA, crops in different reaches, of network of 82 kilometers, for 1 month, the ICA generated, is 26,345 hectares. The duty of water, for crop base period, is equals to 0.55 liters, per hectares, per second. Therefore for 15.5 cubic meter, per second discharge, we get, an ICA equals to, 28,182 hectares. For 17.5 hours pumping, the number of fills will be equals to 11.04, and for the whole month we get 331.46 fills, that is 22.23 days, continuous pumping, per month, for 30 million cubic meter of water pumped, per month. The crop water need can be calculated using standard tables, published in FAO, Chapter 3 and 4 publications. For example, a maize crop, with base period 110 days, knowing evapotranspiration in base period, with medium humidity and high wind speed, referring the growth stage table, and crop coefficient table, KC stage, solving the problem for crop water need in millimeters per month considering the rainfall, we get water depth per month, as shown in table Irrigation water frequency is to determine the scheduling of the crop watering, the number of watering, in specified period, and amount of water depth applied. We should take into account the type of soil, infiltration rate, available water capacity, effective rooting depth, permanent wilting point, current watering depth, requirements of the plant, as per consumptive use of water by crop, amount of allowable moisture stress which may be placed on the plant so to have healthy plant growth, to have maximum yield of crops. Timing to take advantage of projected rainfall. The aim in irrigation scheduling is to apply enough water to fully wet the plant's root zone, while minimizing overwatering, and then allow the soil to dry out in between watering, to allow air to enter the soil, and encourage root development, but not so much that the plant is stressed beyond what is allowable, that is maximum allowable moisture level, below which watering to crops needed. In this example, we get frequency of 10.53 days for 600 mm root zone depth, with field capacity 27%, and permanent wilting point at 10%, with consumptive use of crop equals to is 5.58 mm per day. And also the discharge of canal should be designed for peak core watering for small durations. If we design the canal for a base period of 110 days, with water depth equals to 450 mm over the 800 hectares area, we get Q equals to 0.378 cubic meter per second. If we design the canal for a base period of 4 weeks, with water depth equals to 153 mm over the 800 hectares area, we get Q equals to 0.506 cubic meter per second. If we design the canal for a base period of 15 days, with water depth equals to 153 mm over the 800 hectares area, we get Q equals to 0.944 cubic meter per second. So, canal should be designed for peak demand. In short durations, the core watering must be done in a limited period, that is in core period duration. In limited time, certain quantity of water has to be applied to crops. The discharge capacity of canal should be sufficient to supply the required discharge during core period. For constant irrigation interval, say 10 days, and watering numbers equals 3 in a month, we have to supply variable water depth according to need. If watering depth is constant is equals to 10 mm or 25 mm, then number of irrigation as well as interval in days is also varying according to core depth of water. Point to be noted is, no overwatering to be done, neither it will drain off from soil root zone, as well as no long interval to avoid plant stress for development. Merits: multi-level pool irrigation system. 1. Maximum ICA created, as no bedfall in canal. 2. Maximum efficiency, as no wastage of water. 3. Water sharing among users is equal. 4. Maximum yield, as no over-irrigation. 5. Controlled discharge, no overtopping of canals. 6. Time management, as per schedule. 7. Power saving, as demand pumping is practiced. 8. Less labor cost for operation of gates. 9. Overall control over the network of canals by SCADA system. 10. The extra ICA can be generated due to saving in water. 11. Any section of canal can be filled using pilot feeder pipelines connected from delivery chamber or from upstream side canals. Merits over conventional system. Travel time required is only 1 time during first filling the tanks all along the stretch of network. Any section or pool of canal network in any reach, may be upstream of canal network or at tail end, can be filled with same amount of time. No travel time needed. Full supply level in all pools. Always maintained at FSD level. Easy maintenance of any section or pool throughout the year. For silt removal or repairs. No wastage of water to escape channels or to nulhus. Crop pattern and water scheduling can be implemented. Easy measurement of evaporation and seepage losses. Easy management as controlled discharge as per requirement and demand or as per schedule published. No overtopping of canals. Farmer at tail end will get same quantity of water as of upstream reach canal farmers. Water for animals is always available in canals in summer season for drinking purpose. SCADA system for sluice gate, or main canal orifice gates, operated with actuators, controlled remotely, sitting in server room, with use of radio signal, transmitters and receivers, and solar energy supply for operation. Study. To learn the complexity of operation. Need for study. The large network with kilometers of main canal network has to be designed with different lengths of pools at various split levels varying from 1 meter to 2 meter difference in bed levels, according to the outlets in their respective reaches and requirements of water and timing of operation. All the outlets of distributaries have to be designed for constant head to a minimum operating head. Time, and scheduling of opening and closing of the canal main gates, and water transfer, as well as filling time has to be studied with respect to number of outlets in that reach. The crop pattern and scheduling has to be prepared. The velocity in canal, orifice, transition, stilling basin, discharge in multi-level pools, and outlets to be physically studied on models, or modeled in computers using CFD. Physical model study on multi-level pool irrigation system has to be conducted to solve the vast network problems and number of outlets to be handled.
Computer model study eliminates reduced scale physical modeling. Comprises of study and simulation of various characteristics of fluid, namely, velocity, discharge, dynamic surface profiles, flow depths, time, sedimentation and scour, overtopping, inundations of lands, flow measurements, temperature, and pressure. Computational fluid dynamics. The advantages of CFD simulation are that it takes less time than physical modeling and avoids the scaling effects of friction, turbulence, air entrainment and release, fluid structure interaction and local scour below energy dissipators, because everything can be modeled at full scale.
Benefits of CFD, canal operation, and simulation models are very efficient tools for improving the design and operation of irrigation canal systems. We can compare various design alternatives for the development and tuning up of operational strategies and automatic control algorithms. Available softwares are as under: ANSYS, Fluent, Flow 3D, Phonix, Star 3D, OpenFOAM, OpenFlower, Maya, RealFlow, COMSOL Multiphysics, TechPlat. CFD consultants are as listed below.
Simulation. The representation of characteristics or behavior of one system through the use of another system, especially a computer program designed for that purpose. Here are some examples of CFD simulations applied to weir, dam, spillways to get downstream discharge, velocity and flow depths in the valley.
Canal modernization is often thought to mean lining two canals. In actuality, canal modernization is much more than that. To better explain this, we can compare the spigot or faucet at your house to an irrigation canal system. At your faucet, water can be delivered exactly where you want it, when you want it, and at the exact rate you want it just by adjusting the faucet handle. It is not that way with an irrigation canal. With a canal system that is not sufficiently modernized, water must often be ordered days ahead of time. It does not necessarily arrive at the time or rate you asked for, and the rate can go up and down quite a lot during the delivery. If you change your mind about needing the water after it is ordered, then it is often too late. The water is already in the system and has to go somewhere or it will overtop the canal. A canal system that is not modernized can make it difficult for a farmer to manage his or her water carefully. A canal modernization program introduces the service concept, making the water delivery as close to your household spigot as possible, accurately delivered, on time, and when you need it. A canal modernization program looks at the whole water management system, and includes various measures, such as renovation of water control structures, electronic, supervisory control and data acquisition, SCADA, systems, automation of water control structures, water ordering and accounting systems, and regulation of reservoirs along canal systems.
Need for automation. Rising irrigation water costs and unpredictable rains call for efficient monitoring and control of open channels. With the advancements in modern automation systems, it has become possible not only to remotely monitor water flow, but also to remotely control water gate positions, which control the flow rate through open channels. Controlling water gates remotely helps satisfy new requirements set by governing bodies for the efficient management of water resources. Optimization and minimization of water to be applied to the crops is essential in irrigation system. Yields of the crops are adversely affected with excess or inadequate water supply. Yields can be considerably increased by adopting proper irrigation management. For proper irrigation management, scheduling of water is essential. As said, irrigation scheduling is the process by which an irrigator or farmer determines the timing and quantity of water to be applied to the crops. The efficiency of irrigation crop yield depends very much on water supply at the time when crop demand. Number of watering on specified interval is to be provided during the growing season. Due to complexity in operating water intake structure, the constant head at offtake structure is an important issue in the irrigation scheme to facilitate measurement and provide constant irrigation water supply. Presently, all offtake structures are manually operated. Target discharges are seldom met due to upstream water level fluctuations, and the operators are unable to cope with the opening and closing of the many direct outlets in distributories, or laterals and distributories gates and the delivery chamber gates, so automation is the ultimate key to modernize and improve overall irrigation project performance. An answer to control discharge with constant head at outlet structures by automating the gate operation through interfacing with supervisory control and data acquisition system, SCADA.
Gate designs. Rectangular, orifice type and radial flume gates.
Rectangular gates. The proposed cell solution results in the efficient management of water through open channels by enabling users to identify various issues associated with water conveyance systems, such as channel leakages, channel blockages, and inaccurate flow measurements. Also, the ability to remotely monitor and control various sites reduces the labor and time associated with site visits. Figure 1 demonstrates the cell solution, where multiple flow control sites communicate to a centralized server using different communications methods, such as serial radios and fiber optics. The data from all of the sites are concentrated in the main server and are displayed on the Supervisory Control and Data Acquisition (SCADA) server. The user can monitor as well as control the sites through the SCADA server without physically visiting the site.
The orifice-type gates use the valves for discharge fitted with motors operated remotely by radio signals and solar supply energy. Where inlet is provided with transition, bedfall, silt chambers, and steel grates to avoid blocking of orifice pipes. The discharge can be measured by electronic flow meter to know volume of water flow. The velocity in pipe may be on higher side, ranging between 7 to 8 meter per second, so it can be reduced by bell mount outlets and stilling basins. Transition zone. The arrangement of orifice-type gates is incorporated with solution for above FSD discharge. If any gate fails or manual mistakes, extra water is to be transferred without any interference by the overflow weirs provided in the middle of the assembly, extending into downstream side pool. Water scheduling and planning.
Irrigation scheduling is the process used by irrigation system managers to determine the correct frequency and duration of watering. The following factors may be taken into consideration: soil infiltration rate, soil available water capacity, effective rooting depth of the plants to be watered, current watering requirements of the plant, amount of allowable moisture stress which may be placed on the plant, timing to take advantage of projected rainfall, timing to avoid interfering with other activities, such as sporting events, holidays, lawn maintenance, or crop harvesting. The goal in irrigation scheduling is to apply enough water to fully wet the plant's root zone, while minimizing overwatering, and then allow the soil to dry out in between watering, to allow air to enter the soil and encourage root development, but not so much that the plant is stressed beyond what is allowable. In recent years, more sophisticated irrigation controllers have been developed that receive evapotranspiration input from either a single on-site weather station or from a network of stations, and automatically adjust the irrigation schedule accordingly. Other devices helpful in irrigation scheduling are rain sensors, which automatically shut off an irrigation system when it rains, and soil moisture sensing devices such as capacitance sensors. Planning, use of GIS mapping softwares. GIS is a relatively broad term that can refer to a number of technologies and processes, so it is attached to many operations in engineering, planning, management, transport or logistics and analysis. Modern GIS technologies use digital information, for which various digitized data creation methods are used. The most common method of data creation is digitization, where a hard copy map or survey plan is transferred into a digital medium through the use of a CAD program and georeferencing capabilities. GIS accuracy depends upon source data. Paper maps that are not found to be very suitable to achieve the desired accuracy in developing a digital topographic data base for GIS. Topographical maps are the main source of aerial photography, and satellite images are extra sources for collecting data. GIS data represents real objects such as roads, land use, elevation, trees, waterways, etc., with digital data determining the mix. Real objects can be divided into two abstractions: discrete objects, for example, a house, and continuous fields, such as rainfall amount or elevations. Traditionally, there are two broad methods used to store data in a GIS for both kinds of abstractions: mapping references, raster images, and vector. Data capture, entering information into the system by paper maps, can be digitized or scanned to produce digital data. Survey data can be directly entered into a GIS from digital data collection systems on survey instruments using a technique called coordinate geometry. Remotely sensed data also plays an important role in data collection and consist of sensors attached to a platform. Sensors include cameras, digital scanners, and lidar. Improvement to network. Geosynthetic liner used in a canal to prevent seepage onto adjacent lands. Drip irrigation for water application to crops, thereby lot of water is saved. A weir constructed to look after extra discharge in canals. A Portland, Oregon-based startup is adding a new form of distributed generation to the list. In pipe hydropower, anyone with a big pipe, a water utility, a wastewater facility, an industrial facility, an irrigation system, can install a system from Lucid energy, to generate electric power from the movement of the water. Level control valve is a hydraulically controlled, diaphragm-actuated control valve that shuts off at preset reservoir high level and fully opens in response to an approximately 1 meter level drop, as sensed by the three-way altitude pilot mounted on the main valve. Water level indicator with magnetic sensor and electric hoisted sluice gates.
Organization and their cost-effective outputs. Water use efficiency is the ratio of crop yield to the amount of water depleted through evapotranspiration. Water conveyance efficiency, water distribution efficiency, both word high for multi-level pool irrigation system. As no wastage due to absence of escape channels and controlled discharge, and reduced seepage by incorporating the LDPE sheet below canal lining. The aim of economic irrigation is to maximize the financial return per unit of water applied or amount of money invested in the irrigation projects.
Research work.
Latin American applied research. Subject, predictive control, with constraints of a multi-pool, irrigation canal prototype. Abstract, embed this paper presents a real-time implementation of a multivariable, predictive controller with constraints, to regulate the downstream levels, at the end of the pools, in a 4-pool open irrigation, canal prototype. The objective of the controller is to maintain the downstream level, at a constant target value, despite inflow disturbances. The controller is designed using a black box identified linear model. The results show satisfactory closed-loop performances. The closed-loop canal must satisfy the following specifications to guarantee the supply to the consumers, to avoid water spillage, and to protect the control structures. 1. Level variations must be less than 15% with respect to the level of the operating points. Second, the gate opening rate should not exceed 1 cm per second and the gate opening limit is 80 cm. The closed-loop, real-time performance obtained with this control has been very satisfactory, and the imposed constraints satisfied, although a simple linear model was used to design the controller. However, it is a subject for future studies to verify if such simple linear models obtained by identification are still capable to reflect all complex phenomena, such as infiltrations, slope changes, frictions, etc., found in actual operational canals. Although our model and prototype may appear to be quite simple with respect to an operational canal, the closed-loop results, which have been obtained, represent a good starting point and show that significant efficiency could be achieved in irrigation canals by using model predictive controllers. SCADA. Examples of system and products. Total channel control registered, a breakthrough in irrigation network automation. A breakthrough in both irrigation control and flow measurement. The system is based on the control of large networks of solar-powered canal regulators and gates, which are linked through radio telemetry and advanced computer software to enable the whole canal network to operate automatically and remotely.
SCADA products.